school had to satisfy a set of requirements which included providing clean water, having 3 classrooms for 40 students, and having toilets and sinks. In order to provide water to the school, we will be collecting rainwater that falls on the roof. The initial ideas for roofing material were corrugated steel and polycarbonate. Steel is stronger than polycarbonate, meaning we would need less bleachers, but the steel would rust, making water unsafe for drinking. As a result of this, we decided on using a polycarbonate roof. Water treatment was next. Chlorination would remove bacteria, however it would affect the taste of the water, and could potentially add toxins if it reacted with the naturally occurring minerals in water. Ceramic filters would keep healthy minerals, but would not remove chemical contaminants, and as it is fragile, it could break given Mexico is in a seismic region, prone to earthquakes. We decided on using a UV filter as it uses a low amount of power and the process is quick. The issue with this method is that it requires water to be already cleaned. The storage of water would be in an underground cistern as it is cheap and keeps water cool, but it is important that the water remains closed from the elements. We chose this as an alternate ferro cement option was prone to cracking and was more exposed to sun's heat.
This is the inside layout of the school. We made it like that for several reasons, one of which is to simplify the plumbing system and make sure we don't add any unnecessary length to our pipes. We added a common area with a canopy and benches surrounding the playground to make the school more social. The green area includes common trees frequently found and are available in Mexico. The position of the buildings and toilets is placed so the staff and students don't have to walk a long distance to get from one to the other. And so if there's a smell from the toilets, then it won't reach the main school building.
With all this in mind, we need to decide how rainwater will be collected throughout the year as it falls on the roof. In our design, the roof is made from solid polycarbonate, undulated and angled as to aid the water into aluminium guttering. This leads to water passing through a leaf eater, denying large waste into the tank, followed by a first flush system that removes 85% of remaining waste and leaves 50% of dirty water for outdoor plants. This system therefore requires cleaning every 1 to 3 months. In terms of storage, after the water travels through the PVC piping, it will be stored underground in a 100,000 litre capacity tank. This occurs after the first flush system and continues to travel to a UV filter where bacteria are killed. Twice daily, 50 litres of water will be pumped into a tank next to the harvesting area for drinking purposes, whilst non-drinkable water is pumped to a 600 litre tank to be used in flushing and washing.
Rainwater enters the system at the rainwater inlet. This water passes through the downpipe leaf eater and into the settling tank. This separates water from much of its sediment and acts as a buffer to allow slower outflows than potential inflows to provide a more reliably manageable flow. The water then enters the pump house room and passes through the first flush diverter. The most sediment-rich water of the first flush is removed by this diverter and exits the system through the wastewater outlet. This initial process ends with the now sediment-free water travelling into the main 100,000 litre tank. Up until this point, the water is pressurized entirely by gravity and processed entirely by its own pressure, without any external power source. This is important because this process needs to occur reliably and continuously at the effectively random intervals of rainfall that occur. Flows beyond this point will require power to function. Water from the main tank undergoes the final stage of processing as close to the time of usage as possible. Every day at 9 o'clock, the diverter valve and pump are manually set by an operator to fill the 600 litre washing tank to 516 litres and the 50 litre drinking tank to 43 litres. 3 hours later at midday, the pump is used to refill the drinking water tank to 43 litres. Whenever water passes through the pump, it passes through the UV pathogen filter, which contains a UV bulb which lights whenever the pump is turned on. At any time, water can exit the washing tank through the washing water outlet, and water can exit the drinking tank through the drinking water outlet. This process creates 3 water supplies. A washing water supply that at any given time has been sterilised by UV within a maximum of 6 hours before use. A drinking water supply that at any given time has been sterilised by UV within a maximum of 3 hours before use, and a wastewater supply that can be used to water plants. Our float switches will be fitted at the point in the drinking water tank where the water level would be at 43 litres, and the point in the washing water tank where the water level would be at 516 litres. When the level of water reaches these switches, the float is pushed up, which closes the switch, allowing a voltage to pass across it. On the circuit diagram, 2 float switches we intend to use are marked A6 and B6. Switch A6 will sit in the washing water tank, and switch B6 the drinking water tank. Components 1 to 4 in both sections A and B are responsible for taking Mexico wall power and converting it to a 15 volt DC current. When a float switching section A is closed, this will complete the section, powering the indicator LED and a linear actuator. This means that if the washing water tank is at 516 litres, actuator A7 will be powered, and if the drinking water tank is at 43 litres, B7 will be powered. The section of the circuit labelled C is responsible for powering the pump, labelled as C7 on the circuit diagram and 11 on the rainwater treatment system diagram. This circuit is controlled by 4 switches. 2 of these are push-to-brake switches labelled C5 and C6. These are actuated by the actuators in sections A and B. If the circuit is set to throw through one of these PTB switches, the circuit will be broken if that switch is actuated. The switch labelled C3 is an on-off switch, and the switch labelled C4 is a 3-way switch attached to the diverter valve labelled as 10 in the rainwater treatment system diagram, in such a way as to send a current through C5 when the diverter valve is set to fill the washing water tank, and through C6 when the valve is set to fill the drinking water tank. Due to the layout of the circuit, if the operator turns the pump on to fill a tank and that tank reaches its intended storage threshold, the PTB switch that the current was passing through up until that point will be automatically actuated, breaking the circuit and cutting off power to the motor, meaning that neither tank will be overfilled.
There will be 2 of each urinal and toilet for each sex. The urinals will be flushed and cleaned daily by the water stored in the 600-liter tank. No electricity or water will be required to flush, since the collection tank will be placed in a position where gravity will be used as the flushing function. The urine that will be collected will be heated and distilled in an oven at 100 degrees Celsius to extract the water in it, where it will evaporate and be poured in a container for later watering of plants around the school. The toilets will be placed outside, and while being used, the feces will be separated by the urine using a sloped mesh, so the urine can pass through and be collected as well. Once the feces are collected, they will be transferred to an oven, where they will be heated at 90 degrees Celsius for 30 minutes, using 4 kilowatts of electricity to kill any harmful bacteria or pathogens. As the feces become a fertilizer, they will later on be used on the plantation of the school, but very carefully, as to have no contact with any products from the plants and trees.
With our model, we were able to figure out how excess water could be repurposed for months with large demand. And moreover, the year would end with more water stored than how it started, which allows for emergency storage in case of drought or sharing with the community.